Hi Jobbies, welcome back. We continue with our introductory lesson to oscillations. So in the previous lesson, so this is part 1b. I'm taking it that we are done watching the first one. So just a recap, we derived this formula for acceleration, and we took note of the spring, the restorative force. Yeah, so this Fs is for restorative force, and this is the force under Newton's law. Okay, so before we can proceed, we can have an example under this, and then we now go to the business of this lesson. Okay, so let's quickly answer an example. Okay, so here we have a 0.35 kg object attached to a spring of force constant this. So they're telling us the constant, the value of k. Okay, so it has that force constant and then it moves on a frictionless horizontal surface. If the object is released from rest at x is equal to 0.1, find the force on it and its acceleration at this point, this point, this point, this point, this point. Okay, so what I don't know if you're able to see, but let me quickly run you through. So like they have given us a certain object that has that mass with this spring constant. So they are telling us to find the force and acceleration at different positions. Okay, so we start with the first one. So like this is our, so this would be the equilibrium, and then the object is somewhere here. So it can be given in form of a pendulum. The principle remains the same. So at the first point, they are telling us that the value of A, the maximum displacement, is 0.1 meters. So they want us to find the force and the acceleration. So how do we find the force? We simply say the force is equal to negative kx. So we're going to have negative, what is the value of k? The value of k is 1.30 times 10. So the 0 you can omit it, times 10 power 2 Newton meter, times the value of x here. What is the displacement? The displacement is 0.1. So what is the force you are getting? If you do your calculation, you'll get is it negative 13? Okay, so I found negative 13. I hope my answer is correct. My calculator is made in Lusaka, so don't be surprised. So 13 is our answer. So the force is in Newton, negative 13 newtons. And then what about the acceleration? Acceleration is equal to negative k over m times x. Is this the formula? Oh yeah. So we derived this when we equated from Newton's second law of motion. So the spring constant is the spring constant is 1.3 times 10 power 2. The value of x was still dealing with this position 0.1. Oh yeah, so this is over m. M is the mass. What is our mass? They gave 0.35, so we say 0.35. so you can do the math. I know here things might not be clear, but you're able to hear me. So what is this? Divide by that, and then the answer times 0.1. We're getting negative 37.1 meters per second squared. Okay, so that's how we answer. So we've answered at this position, at the first position here, when x is equal to 0.1. so you finish up. Okay, so I'll do also for this one. Yeah, so what about when we reduce the displacement, when we take it to 0.05? And then what about when we say negative 0.05? What will be the values? Yeah, so for the next one, we have a spring like that, and then this is the equilibrium. So on the next one, they're giving us 0.05 as the displacement. So you can obviously find the force. You say negative kx. So k is, they already gave k, which is 1.3 times 10. And then x, it is 0.05. Okay, so you can compute this. We're getting about negative 6.5. That's the force. And then for the acceleration, you do the same. You write the formula. You're going to get, so acceleration is equal to negative k. We know k, we also know m, and we know x. It's just substituting. So you get negative 18.6. So this is actually an exam question. Although it didn't come like this, they just listed them down. Yeah, so the only thing here is that it can get boring, like you're just repeating the same procedure. If they want, they can give you like 6 values. You find the force, you find the acceleration. Yeah, so it's just your duty to solve and get those marks. So, and the common question here, they didn't even ask. Yeah, they didn't. So there can be a follow-up question where they tell you that what is the relationship? What relationship can you observe? So what we're going to observe here is that this was 0.1, this was the displacement 0.1, but here it's 0.05. So I've reduced the extension. So like that one, it was 0.1, meaning it was somewhere here, but we have reduced. So what are we observing when we reduce? When we reduced the extension, this one, the number became bigger. Negative 6.5 is larger than negative 13. So when you reduce the extension, so when the extension is reducing, the displacement is reducing. In this case, the force will be increasing. Yeah, so that is the relationship you are able to observe here. When one is reducing, the other one is increasing. Yeah. And then what about the acceleration? Even the acceleration, when we are reducing the acceleration, when we reduce this, the displacement. So when the displacement was big, when it was 0.1, the acceleration was negative 37. But when we reduced the displacement to 0.05, the acceleration became negative 18. So negative 18 is bigger. So you'll be able to see these very nicely when you do the others as well. So where there is x, what if you put 0? What are you going to get? What if you put negative 0.05? What if you put negative 1? You actually find that the numbers even start becoming positive, because the more x is becoming negative, the more the force will be becoming positive. Okay, so that was just that. A very important concept there. So we can now go to the business of the day. So we want to discuss elastic potential energy and velocity as a function of position. Okay, so elastic potential energy. What is this elastic potential energy? So elastic potential energy, which is, so the symbol for elastic potential energy, we'll write it like this, PE, and then we put delta S, like a small delta S. So in the introductory lesson of the first video, I said the elastic potential energy, this, so this is potential energy that is elastic. So the elastic potential energy is similar to the strain. You can even say it's the strain if you like. So what is the strain? We said strain is the energy that is stored in a spring. So when we have a spring like this, when you stretch a spring, it comes to this point. It means like it is now absorbing energy. So that energy which is being stored, it is potential energy. That is the energy which will like work in hand with the restorative force. Okay, so that's it. Potential energy. So what is the formula for potential energy? Yeah, so like I introduced, you just record the formula for the strain. So the potential energy, the elastic potential energy is given by half kx squared. Is that so? Yeah, so that is the elastic potential energy. So it is the energy due to a string. So and then now we have what is called the conservation of energy. So you remember the conservation of energy, the law states that energy can neither be created nor destroyed. Okay, so at this point, yeah, so the under the what we have like mechanical energy. According to the law, the initial mechanical energy is equal to the final mechanical energy. the mechanical energy final. So what are these? We have potential energy. So mechanical energy simply potential energy. We have potential energy plus kinetic energy. So these, their initials, they are equal to the finals when we get the same things. So that's the mechanical energy. Mechanical energy is equal to potential plus kinetic. So this is initial, and then here our final. So the thing now, we introduced this. This is whereby we have now a spring where we're dealing with springs. So we're also going to say, also when we add everything together, the initial elastic potential energy. So this is just gravitational potential energy, and then this is elastic. They are equal to their finals. So I don't have space here. Okay. So this will be equal to the final elastic potential energy. Okay. So what are we saying? Elastic, the initials of elastic, gravitational. So this is potential energy, but the gravitational. No wonder we're putting S. This is for springs. It is elastic. And then, yeah. So we can even remember the formulas. What is the formula for potential energy? Elastic potential energy. It's 1 over 2 kx squared plus this gravitational potential energy. That's why I will say mgh plus kinetic energy. It's 1 over 2 mv squared. So these are initials, they are equal to their finals. Alright, so not so much here to discuss. How about we dive into an example? Let's do this. Oh, and one thing I forgot to mention. So there's a frequent question where they will ask, what is the work done due to the work done due to non-conservative forces? So the work done is simply equal to the mechanical energy final minus mechanical energy initial. This is the work done by non-conservative forces. So I've mentioned this because it's there in the example. Yeah, so the finals we have, they are here, like you know where we'll get them from, and we have those initials. Okay, we can proceed now. Let's discuss this satanic question. Okay, so we have a problem here. I hope that's better. Okay, so we have we're being told that a car. So this question is coming from college physics. Sewe. So we have a car that is 13,000 Newton. That starts from rest and then it rolls down a hill from a height of 10 meters. Okay, so that's our height. And then according to that figure, it moves across a level surface and bumps into the spring. So if we neglect the friction, the rotational rules of the Shan, they're just trying to make life easy. Yeah, obviously, life shouldn't be hard. So the question is, find the maximum distance the spring is compressed. Okay, so find the maximum distance the spring is compressed. So at this point you have to you start gathering your physics. What do we have? Like we have this car, it is at a certain height. So the energy, okay, first when you look at a spring, obviously you should think, okay, there is elastic potential energy. So elastic potential energy, which is written as PE with like a small s. When you just see a spring, you even know, okay, there's elastic potential energy. So we know there is elastic potential energy. And then, so the car is rolling down, it's moving. So what energy relates to motion? It's kinetic energy. You are gathering your physics. And then, okay, so like it's at a given height, and then it even has a mass, and obviously there is gravity, so something should click. We have this such, so they are indirectly telling us that we have potential energy. Okay, so if you think in these lines, life should physics should be less stressful. So at this point they're asking us to find the maximum distance that the spring is compressed. So what is the maximum distance? So given these things, then we should be able to say, okay, then the initial elastic energy, the elastic potential, plus this initial, the initial potential energy, so this is gravitation, and the initial kinetic energy. Oh, I'm already writing the formula. Kinetic energy. So these are all to my initials. So instead of writing initial, you can simply just put everything in brackets and then you write initial outside. Yeah. So these are the initials. So the initials, according to the conservation of energy, they are equal to the finals. So the final elastic energy, the final potential energy, and the final kinetic energy. These guys they are equal. So now we just start to think through things. So at this point, hold on. Yeah, so at this point, like when the car was starting, so this is the initial. So initially there's no spring here. Okay, so there is no spring there, here. So obviously you should be able to say then this potential energy due to spring, which is called elastic potential energy. The elastic potential energy, will say it's 0. Yeah, because we're not dealing with a spring here. And then plus the potential energy gravitational. This is why I've gotten the details. So if the car was just straight, we could have removed gravitational, because the mass won't be playing a very big role, and there's no vertical height. The gravity also won't be playing a role. Yeah, so we have gravitational potential energy. So gravitational potential energy is mgh plus. Here the car was starting at rest, meaning it wasn't moving. So this means that kinetic energy was 0 because the car wasn't moving. kinetic energy is 0 like that. Okay, and then so what do we have on the other side? So on the other side again, we start thinking, we look at this one, potential energy due to spring. Yeah, so the car bumped into the spring, so obviously we have potential energy due to the spring. So we say half kx squared, the formula for this, plus here now potential energy. It won't make much sense, like, oh, so when we put this, like, so what is the height when the car is down here? What would be the height? The height is 0, so no wonder this will remain 0. So here down now, there is no gravitational potential energy, so under gravitational potential we put 0 plus, so now this is why we have kinetic, because the car now obviously it was moving, speed, it was rapid. So we'll say what is kinetic energy? It's half mv squared. So having collected our data, or having substituted the formulas, we can now plug in the values. What is the mass? So the mass is yeah, where's the mass? We can't see the mass. Oh, so at this point, I've remembered one detail. Okay, so here the kinetic energy which I got, like assuming the car was moving, so it had kinetic energy, but when it bumped into the spring, was it still moving? Yeah, so like here at this point, the kinetic energy wasn't there because the car wasn't moving. So like kinetic energy, it's half mv squared. So the final velocity here is 0 because it's not moving. So under kinetic energy, we're putting 0. So let's put plus 0. Yeah, so that's under the kinetic energy. Okay, so at this point we can collect like terms and make the subject of the formula. So what do we have? We have mgh is equal to half kx squared. So we want to find this value of x. What is the value of x? So we're just remaining with saying this is half kx squared is equal to mgh. So we have kx squared, so this is over 2, 1 times 1, 2 times 1, mgh. So we can cross multiply, so meaning here of over 1. So we're going to have kx squared is equal to 2 times these guys, it will be 2 mgh. And then we want to remain with x alone, we divide by k, even here by k. So we're going to have x squared is equal to 2 mgh over k. And then finally we can get rid of the square root. Okay, so I'm teaching you like babies. Yeah, my job is. So to get rid of this, we say this is 2mg over k. So the question was, yeah, I'm sure you understood the question. It was what was, how far was the spring compressed? Yeah, no wonder we were making x the subject. So the question is, find the maximum distance the spring is compressed. Yeah, so simply finding the maximum distance there. So at this point, this is why you would start sweating in an exam. So some things you just have to think through, and other things you get to learn through experience, like the way you see here. So like we are not given the mass. This mass wasn't given. So you even start crying like, yeah, I've been using the wrong formula. So we haven't been given the mass, but we have been given a particular force. They've told us that force is equal to 13,000 newtons. Yeah, that's the force, not so. Yeah. So, and then what do you know about the force? You know that the force is equal to ma. And then also, if not ma, we can put it as mg. This is the weight. They are the same. So where you are seeing that we have mg, you can actually put this 13,000. So meaning we're not going to sweat to look for mass. We're just going to say this mg together, gravity times mass, is equal to the force. Okay, and then is the spring constant given? For the height, we know they gave us 10 meters. Yeah, we're at 10 meters there. Spring constant, it's here 1.0 times 10 power 6. Okay, so what's remaining is just substituting. So square root over 2, the force 13,000, and then height 10 meters over here, over the spring constant 1 times 10, 1 times 10 power 6. So you just punch that on a calculator. You say 13,000 times 10 times 2. You divide by everything. So did you calculate? What answer have you gotten? I'm getting 0.5099 blah blah blah. So you usually leave your answer to 3 significant figures. So this can be 0.51 meters. Okay, so this 4 marks is you have to earn it. So what else do we have? Calculate the magnitude of the car's maximum acceleration after contact with the spring. Okay, so what is the car's maximum acceleration after it is in contact with the spring? So at this point, the car has collided into the spring. The spring was there, and then the car went in. So what do we remember about acceleration due to a spring? We said negative k over m, negative k over m x. So I think the compression, we know it, the value of x. So the value of x, we've calculated it 0.51, and then k, we have been given k. So the problem is m. M can make you sweat. So let us learn another skill which you should apply in case things they give you such satanic questions. So this is negative, we say kx over m, like that. And then at this point, what we have, so here this is m. This is m, but we haven't been given a mass. So we just have to think of a way like, why can't we just put g so that this becomes a force? So we can't just put g like this, like we are crazy. So we are going to say we multiply by g over g. So this means that like g over g is 1. So we haven't changed anything. And like you just put g alone, then you're changing the meaning. So acceleration is equal to negative kx and then times g. Even here, m times g. The g's can cancel, but this time we don't want them to cancel because we want to use it. So this will be equal to negative, the value of k, it is 1 times 10 power 6. 1 times 10 power 6. And then x is the compression, we found it to be 0.51. And then gravity, we know it is not 10 over mg. I have a problem with writing this car over. Okay, so we know mg, it is the force, which is 13,000. So you can now you can now punch in the values. What are you getting? It should be around 380. Negative that. Yeah, so that's our acceleration. So acceleration is a vector quantity. It can be negative or positive. So for such questions, we can say the modulus of the acceleration so that we remain with a positive answer. Meters per second squared. Okay, so we've answered that question. Are we still going? What else? If the spring is compressed by only 0.3, find the change in mechanical energy. Oh, they've taken us back to this. So let's quickly find the change in mechanical energy. Okay, so our physics is for solving. So they are telling us that. So let me just display the question again. Okay, so they are saying if the spring is compressed only by 0.3 meters, what is the change in mechanical energy? So, or at least they've even told us what is the change. They can say what is the work done by mechanical energy. So the change in mechanical energy, or they can write work done. I'm emphasizing that because things are not always the same. They'll just change to a few things, but the concept remains the same. So change in mechanical energy, we say the energy in the spring plus the gravitational energy plus the kinetic energy. So these are the finals. So the finals minus the initials, that is the change. Spring, gravity and kinetic energy. Okay, how my students will understand. So what is the energy in the spring? The energy due to the spring here we have, so we're going to say the elastic potential energy is half m. The energy in the spring is half kx squared plus potential energy. Here we don't have potential energy, there's no height for the car, it was just here. So we can write the 0 without putting no mgh, and then the kinetic energy is 0 as well, minus what do we have? So these are now initials, where we are coming from the initial values. So we didn't have elastic potential energy, 0, plus gravitational potential energy, PE, we had here, because gravity is playing a role and there's a height. Kinetic energy, it's not working like your mobile money balance. Not working. How can you have 0 kwacha? Okay, so we're going to say this is half kx squared minus mgh. And then what are we going to have? 1/2. The spring constant, they told us it's 1 times 10 power 6. And then the value of x, they said it moved there. Can you see here? It was what if it was compressed only by 0.3? Okay, and then the mass and gravity together, they make a force. I think you have now mastered the art. And then we'll have 10 there. So you do your math, you are going to get negative 8.5 times 10 power 4. Yeah, so these are in joules. So that is the change in mechanical energy. Is that okay? Yeah, so we can. So on this one, make sure you go through on your own. Go through this question. Yeah, practice. You can even look for some similar questions on the like. So we proceed. So what did we set out to look? We said we'll look at, so we finally done that. We're now remaining with this velocity as a function of time. So let's go to the last part. Velocity as a function of time. So on this one, we're going to derive the formula if an object undergoes a quarter of a cycle. Yeah, so I think I can I gave you an exercise. I don't know how many tried that. So we're discussing this in the introductory video. So what you have to know is that when an object moves from here up to here, this is quarter, and then when it goes to the far end, this is half. When it comes back, this is 1/3 or 3/4, and then how do you write? Yeah, and then when it goes there, that's when it makes a 1. Oh, so this is 2/3, not 1/3, 2/3. Yeah, so I just want to tell you that this is a complete oscillation. It goes. Remember, the topic is oscillations. This is one oscillation. So when I tell you 2, it means when it comes here again, it starts going half, quarter, qua. Yeah, so there's a lot. So now for the velocity as a position of velocity as a function of position, here we will consider a quarter of a full oscillation. So we have our point there. So what happens when we stretch the spring to the far end there? When we stretch the spring to the far end, then what we're going to have is do you have kinetic energy here? So like let's remember the energies we're from looking at. So we have here, so we have potential energy due to the spring, we have potential energy due to gravity, and kinetic energy. Yeah, so when the box is at this point, it's not moving, so it doesn't have kinetic energy. And then it is just on a frictionless surface. It is on a surface that doesn't have friction, ideally. So it is just on level surface, meaning there is no height. Yeah, the mass is not taking part. Yeah, so there's no potential energy at this point. So what we have is only kinetic energy, elastic potential energy, the energy due to the spring. That's what we have at this point. So what are we going to say? We're going to say at this point, the only energy we have is this one, potential energy due to the spring, or elastic potential energy. So what if now it starts going back, like it comes to a certain point like here? What it will have, it will still have some elastic potential energy, and then since it's moving, it will have some kinetic energy. But for the gravitational, it won't be there because we don't have some height. Yeah, the mass isn't important here. So when it starts going back, it has two things: elastic potential energy and kinetic energy. So we're going to equate these two. So we say this is that so? Yeah. So one thing I didn't mention nicely. Okay, so this was the maximum displacement from here up to there. Yeah, so the maximum displacement, we write it as A. And then now it goes back, but it doesn't get back to equilibrium. It just reaches somewhere here, and I've put the R up to this point, meaning this is just X. Yeah, the maximum is the amplitude. So like if it reached here, we would have written, okay, this is A again. Yeah, but it is at some point, so we just write x. Okay, so when we equate, what do we have? When we put it at, when we stretched it at the far end, we only had the elastic because it wasn't moving. So now when we release it, we're going to have kinetic energy because it's moving. And then since that's when it was just released from the spring, it means it still had some energy, the elastic energy. So plus the elastic energy is PE and the S. So at this point we're going to substitute. So we're going to say this is half mv. In the spring it's half kx squared. So but if you see, this is the maximum displacement, so instead of writing x here, we write a squared as the maximum displacement. So this will be equal to kinetic energy. We know it's half mv squared plus potential energy due to the spring when it was coming back. We say 1/2 m. We can't put a because it didn't reach equilibrium, so we just put x. We put x like that. So after doing this, the heading is want to know the relationship between velocity and position. So let us make v the subject of the formula. So and then before doing that, we can see that we have 1/2, 1/2, 1/2. So that means we can cancel it out, or we're going to say we multiply by 2, so that 2 can cancel with these tomatoes. You go away, go away. So we're going to remain with kx squared is equal to mv squared plus this is a square plus mx squared. So to make v the subject, we can take this to the other side so that we just remain with this. So what are we going to have? We're going to have k a squared here minus this mx squared. Why was I writing m? So the formula for the spring energy is k. Okay, so this is kx, and then even here this is kx squared. It's the spring energy. So all this is kx. Yeah, so remember to always rewind. You can replay the video, screenshot where you seem lost. Yeah, so but I take my time to explain so that at least you follow through. So mv squared there, and then we're still making v the subject, so we can divide by m. Divide by m. Even here we divide by m, so that we're going to have ka squared minus kx squared over m. So over m. So this is equal to v squared. So having that, we're going to be like v squared we're going to say v squared is equal to ka minus kx, so these are square, over m. And then we can get rid of the square on v. So I'm going to say v is equal to plus or minus. When we cancel it out, we're going to have k. So here we can factorize. You can see that we have two k's. We have this k and we have that k. So we can factor them out. We can factor out k, so that we just remain with a squared minus x squared. So the whole lot of this is over m. Yeah, so but we put the k over m here. Remember, it's just down here, so this is like this over 1. So m is over everywhere. Okay, so this is the relationship of velocity and displacement. Very important. So this is the maximum displacement, and then this is some other distance when it came back. Yeah, and then about the signs, the signs, velocity can either be negative or it can be positive. Yeah, so if the object is moving to the right, velocity is positive. Like if the object is moving like that, we use this formula with a positive. If the object is moving to the left, we use the formula with a negative. The answers will be the same, just the sign that it's the one which will be different. Okay, so now as we come to conclude this lesson, let's quickly tackle tutorial sheet questions. Should we do that? Okay, so now we're going on yet another break. Okay, me, I like going for break. I like going for breaks. You guys, like, I'm thirsty. Can you see the time here? Oh, yeah, 04. Yeah, so we'll take a short break, and then we come and continue. So for now, it's bye-bye. So we're done with the lesson. Yeah, we've answered everything, or we've learned everything we planned to. Yeah, up to this point. So I just like showing you the application in form of, okay, since we have answered this, you can tackle that. Yeah, so let's do some practice questions so that they enhance your understanding. So this was lesson Oscillations lesson 1 part B. So watch out for part 3. So I'm just going to answer 2 questions and then we'll be done. Okay, and then we look out for lesson 2 where we go even further. So for now, bye bye. See you in yet another lesson.